Okay, welcome to the math lesson today on triangles and the Pythagorean theorem. So triangles, the simplest of all the shapes, that it only has three sides and three angles. So when we describe a triangle in math, we label the three angles that make the triangle with capital letters. So for example, this triangle we would describe as triangle A, B, C. Three angles with capital letters. And then the sides that are across each of the angles we label with lowercase letters. So this is big angle A. Across from it would be the side little a. Similarly, if this is angle big capital B, side from it would be little b, and then little c. So the side lengths we label as lowercase letters. One of the unique properties of triangles is that if you were to add angle A plus angle B plus angle C, so all three angles of any triangle, you always get 180 degrees in total for the angles within a given triangle. So no matter how the triangle is drawn, the three angles of the triangle always add up to 180 degrees. That's an important idea in geometry with triangles, and we see that a lot when we get to geometry. Of all the different triangles in the world that exist, one of the special triangles that we deal with a lot in math is the right triangle. What makes a right triangle is that one of the angles in the right triangle is a right angle, hence the name right triangle. That means one of the angles has an angle measurement of 90 degrees. You can't have more than one angle be 90 degrees because, again, all three angles in the triangle have to add up to 180. So if you have two of them at 90 degrees, you'd absorb all the 180 degrees and there'd be nothing left for the third angle. So one angle is 90 degrees, and that's usually noted by that little box here. It tells you that that's the right angle. And in a right triangle, the sides have specific unique names to them. The two sides, so here's triangle again, A, B, and C. The three sides of the triangle have unique names. The two sides that create the right angle, so here's our right angle, is made by this side and this side. In a right triangle, we call those legs. So two legs of a right triangle. They form the right angle. The third side of the right triangle, so you have two legs. The third side, by default, there's only one side left. We call that the hypotenuse. So two legs and a hypotenuse. The hypotenuse is always the longest side. And its longest side because it's opposite the right angle. The right angle is 90 degrees. It will always be the biggest angle. Therefore, the side across from it will have the longest side. That's the relationship between the angle measurements and the side lengths of a triangle. So two legs, we call them leg 1 and leg 2 respectively. And then the hypotenuse, we abbreviate that HYP for short in math. So two legs and a hypotenuse. Alright. The Pythagorean theorem relates the three sides of a right triangle. And it's only used with right triangles. Once again, here's our right triangle. The three sides of a right triangle are related by the Pythagorean theorem in that, let's say we're going to call this little side A, little side B, and then the hypotenuse is side C. Again, the hypotenuse is the side across the right angle. And the Pythagorean theorem says that if we take the length of this first leg, so the length side A, and square it, and then add it to the length of the second leg, we'll call that side B, little b, and square it, it is equal to the length of the hypotenuse squared. Most students remember it as a squared plus b squared equals c squared, and that is basically the Pythagorean theorem. And you use that frequently in math, especially in geometry, in dealing with right triangles and finding different side lengths. Pythagorean theorem. How it's used in practice is, say for example we have this side is 3, this side is 4, and we are asked to find that missing side, the hypotenuse. We're going to call that little side C. It's a variable, you can call it anything you want. And if we apply the Pythagorean theorem, and we can only because it's a right triangle, it says that, well, 3 squared plus 4 squared is equal to the two legs, again, squared plus each added together, is equal to the hypotenuse squared, c squared. Order of operations, we do the squaring stuff first, so 3 squared is 9, plus 4 squared is 16, equals c squared. 9 plus 16 gives us 25, is equal to c squared. And anytime we want to undo something squared, we square root both sides. And so the square root of 25 is 5. So the missing side c is 5 units long by Pythagorean's theorem. That combination of side length 3, other side length 4, hypotenuse 5, we call that a 3, 4, 5 triangle. We call those Pythagorean triplets. They match, or they fit perfectly into Pythagorean's theorem. Not all right triangles fit nicely in terms of Pythagorean's theorem and the Pythagorean triplets. Sometimes you have triangles that look like this. Let's say, for example, we'll call this 8, and we'll call this side 5, and then we're asked to find this missing side of the right triangle. We can call that, for example, A. Again, they're variables, you can call it whatever you want, but the most important part is that you set up Pythagorean's theorem correctly, in that you say, well, 5 squared plus this side I don't know, we're going to call it A squared is equal to 8 squared. So leg squared plus leg squared plus leg squared, so the two sides that form the right triangle, those are your legs. Add them together is always equal to hypotenuse squared. Okay. And our job now is to find out what that missing side A is going to be. So little algebra gives us 25 plus A squared is equal to 64. Subtract 25 from both sides. So A squared is equal to 64 minus 25 gives us 39. And then again, to solve something squared, we take the square root of both sides. So A is equal to the square root of 39. And then again, here's an example of something that's not a perfect square. You can leave your answers in radical form, or you can go to the calculator and find out what the square root of 39 is. But just for a discussion without the calculator, the square root of 39 should be a number somewhere between 5 and 6, because 5 squared is 25. And 6 squared is 36. No, I'm sorry. That should be somewhere between 6 and 7, rather. Square root 6 squared is 36, and then 7 squared is 49. And that makes sense because, remember, the longest side of this right triangle is 8, so this missing side here can't be bigger than 8 because 8 again is the hypotenuse and it's always the longest side. So this missing side, square root of 39, some decimal somewhere between 6 and 7. And we'll look at another example of Pythagorean's theorem. And doesn't matter how the triangle is drawn or oriented, as long as you have a right angle in it, it becomes a right triangle for us. And we can apply Pythagorean's theorem to it. And for example, this one, we're going to find this missing side here. We can call this b for the sake of discussion. And if we apply Pythagorean's theorem, again, it's leg squared. So 4 squared plus b squared is equal to 7 squared. That's 16 plus b squared is equal to 49. And we subtract 16 from both sides. So b squared is equal to 33. And then we're going to take the square root of both sides. So b is equal to the square root of 33. And as a check, the answer that we get here has to satisfy the equation that we built there, because what an equation again tells us algebraically is that this value on this side of the equation must equal the value on that side of the equation. So if we're saying that the square root of 33 is the side length b, and it must satisfy this equation that's given to us through Pythagorean's theorem. And we can verify that by saying, well, 4 squared plus, well, b we said is the square root of 33 squared must equals 7 squared. This is an equal sign. And it does satisfy the equation in that, well, 4 squared is 16 plus, well, if I were to take the square of the square root of 33, square roots and squares undo each other, if you will, so we're just left with 33 is equal to 49. When we check things, we only work one side of the equation. So 16 plus 33 gives us 49, and it does indeed equal 49. Therefore, it satisfies the Pythagorean theorem because it's a right triangle, and the algebra of the problem works in that their solution balances the equation. The left side is equal to the right side, so the equality is maintained. That's it for Pythagorean's theorem exercise problems. You'll probably work some in your work to practice how you set up the theorem, solve the missing side, and that is it for today.